Hey guys, the objective of this video is to do a variable loading case when beta equals a half and two-way drainage. So in terms of our flowchart, we're coming to a completely new branch. We're looking at variable loading, beta equaling a half, and two-way drainage. So the question said that gravel is being deposited at a rate of 1 meter per month. The unit weight of gravel is given as 10 meters cubed per meter, 10 kilonewtons per meter cubed, and this deposition stops after 1 year, right? Our soil profile is 4 meters thick, and our graph's going to look something like this. So we can work out that the pressure increase, so the pressure per month will equal the depth per month, so it's getting deposited at 1 meter, and the unit weight is 10 kilonewtons per meter cubed. So this would give us a rate of 10 kPa per month, which means that after a total of 12 months, because it stops after 1 year, so after 1 year or 12 months, the total value will be 12 by 10, so it'll be 120 kPa, and that is changing at each time period. So we're first going to go and find our increment of time and then find what that is at each value. By doing that, we need to first find beta. So beta equals CV, change in time on change in Z squared. Let's say for our case the CV was 2 meters squared per year. So we want this again to equal a half because that's a nicer solution to work with. So, and we have a 4 meter profile. A nice value would be to change that into 1. So if we had increments of depth of 1 meter, so 1, and that means our change in time would have to be 0.25. So working this out, we get 2 times 0.25 divided by 1 is a half. So we've found that change in time of 0.25 of a year, which is the same as 3 months, and we found that our increment of depth is 1 meter. So these are nice values to work with. So what we can do now is we can find the stress at any one of these points. So we're concerned about 0.3 of a year, 0.25, which is 3 months, 0.5 and 0.75. So at 0.25, which is 3 months, we would go 10, so it's 10 kPa per month, times by 3 months would be 30 kPa. This similarly would be 60, this would be 90, and that would be 120. So we've found the stress at every single point we're interested in for our increment of time. We would then, as always, come to draw our numerical table. So time, stress, change in stress, Z equals 0, Z equals 1, Z equals 2, Z equals 3, and Z equals 4. So we'd come and let's look at time 0. So time 0.25, these are just our increments of time. So 0.75 would get to 1 year, 1.25, and let's stop at 1.5 years. So we would then rule off these points. Now, the change in stress is actually different at different points. At time 0, the change in stress is 0. At time 0.25, at 3 months, the stress is 30 kPa. At time 0.5, so at half, this is 0.5 at 6 months, the stress is 60 kPa. At 0.75 at 9 months, the stress is 90 kPa. And at 1 year, we get a peak stress of 120 kPa, which is sustained through the rest of its life. So we could then work out our change in stress. So at time 0, the change in stress at a point just before 0 and a point after is both 0. So there's been no change in stress. At time 0.25, at 3 months, we've had a change in stress of we've gone from 0 to 30, so it's increased by 30. At time 0.5 of the year, it's gone from 30 to 60, so it's increased by 30. From 0.75, it's gone from 60 to 90, so it's also increased by 30. At year 1, it's gone from 90 to 120, so it's increased by 30. At year 1.25, it's gone from 120 to 120, so it's increased by nothing, and that's also increased by nothing. A good idea then is just to rule this off. So this is all our data we need. We will then look at our boundary conditions. So we have, in our case, two-way drainage. So we have the excess pore water pressure being allowed to dissipate upwards and downwards, so at the top and bottom, which means that we could fill in our top and bottom layers as 0, 0, 0, 0, 0, and at the bottom it would also be zeros everywhere. And in this case, we also, because we have no stress at time 0, in contrast to the example with the abrupt load, these are also all 0. So now, based on all this information, we can march our solution forward. We know that this is a case for beta equals a half. So when beta equals a half, the formula we use is UB at time 2 equals 1/2 of UA time 1 plus UC time 1, that's in brackets, plus the change in stress. And this change in stress is going to be important now because we actually do have changes in stresses. So if we were to do this one here, so if we were to look at that one, it would be 1/2 outside of UA is 0 plus UC is 0 plus we have a change in stress now of 30 kPa, so plus 30, so this would equal 30. So this would equal 30. All the other values would also be 30. You can do it in your own time. If we were looking now at this case, so UB would equal equal 1/2 would equal 1/2 outside of UA, which is 0, plus UC, which is 30, plus the change in stress at this point, which is 30. So it would be 30 divided 2, which is 15, plus 30, which is equal to 45. So we get an answer of 45. This would be 45, this would be 60, and this would be 45. I'm just going to fill in the rest for you guys. You can do it in your own time if you like. This would be 60, this would be 75, this would be 60, this one would be 67.5, this would be 90, this would be 67.5. I'm just going to do this one slowly because we've got a bit of a difference now. So for here, we're concerned, the same formula, UB would equal 1/2 outside of 0 plus 90 plus the change in stress, which has gone back to 0 now, so we don't have any more change in stress, so it would just be 90 divided 2, which is 45. So this would be 45. We could work out the rest. This would be 67.5, this would be 45, this would be 33.8, this would be 45, and this would be 33.8. Okay, so the important difference between a variable loading case and an abrupt loading case is that we actually are getting a change in stress at our different increments of time. So that influenced this formula, because before we weren't adding on any change in stress when we had an abrupt load which was sustained, but for a variable loading case we do have a change in stress which we need to consider in this formula. So that's the main difference between a variable loading and an abrupt change which is sustained. And you can see that for the sustained part of this load we have 0 change in stress, which is exactly the same way we found the previous example where we didn't include any change in stress because that is 0. So that is exactly like how we did it in the previous video. So just keep in mind, variable loading, you're going to have a change in stress which you have to consider in this formula. Anyway guys, hope that helps.